All right, engineers, grab your coffee, torque your nuts, and loosen up your tolerances. It's time for another episode of Mechanical Engineering Made Simple. Today, we are looking at a pretty fundamental paradox in physical design.
Yeah, a really fascinating one, actually.
Right, like why does the dead center of a spinning turbine blade, the part that is literally moving the slowest, why does it want to rip itself apart the most? And, how does the delicate geometry of a literal soap bubble hold the mathematical secret to preventing a massive solid steel beam from twisting in half?
It sounds completely contradictory when you put it like that.
It really does. And we have a massive stack of structural engineering material on the table today covering, well, everything from the foundational properties of plane areas all the way up to the really dense matrices of composite laminate theory.
And, to the untrained eye, it might just look like this huge mountain of calculus and material science tables.
Yeah.
But underneath all those integrals and differential equations is the hidden architecture of the physical world.
Exactly. So our mission today for this deep dive is to decode that dense, math-heavy language of structural integrity. We're giving you a shortcut to understanding not just how structures fail under extreme loads, but, how engineers meticulously design geometry and manipulate material properties so they absolutely do not fail.
Right, because failure is not an option.
Definitely not. So by the end of this deep dive, you're going to be able to see the invisible stress flows holding up the bridges you drive over and the airframes you fly in.
But before we can even begin to understand complex failures or those really advanced aerospace composites, we have to start with the baseline mechanics.
The fundamentals.
Exactly. We have to establish the foundational relationship between just a simple geometric shape and its inherent strength under a bending load.
So looking at the mechanics of a plane area, the foundational concept is the moment of inertia, right? Expressed in that classic integral I sub x equals the integral of y squared dA.
Yeah, that old friend.
We all know the formula, but the story it actually tells about structural efficiency is pretty amazing. I mean, moment of inertia isn't about how much a material weighs or even what the material is alloyed from, is it?
No, not at all. It is entirely a measure of how the cross-sectional area of a shape is distributed away from its neutral axis.
And the neutral axis being basically the dead zone.
Yeah, it's the calm in the center of the storm. When you apply a bending moment to a beam, the top fibers might be getting completely crushed in compression, and the bottom fibers are getting stretched out in tension. But that neutral surface running right through the centroid
isn't changing length at all.
Right. The stress right there is zero.
Yeah.
So looking back at the integral, the y represents the distance of any small area element from that neutral axis.
Yeah.
And because that distance is squared, any material placed further away from the center contributes exponentially more to the bending stiffness of the beam.
Exponentially more. The way I've always visualized this is as a form of, well, basically structural leverage.
Oh, I like that.
Like, think about taking a standard plastic ruler. If you hold it flat and apply a load to the middle, it deflects super easily, right?
Yeah, it just bends.
But turn it 90 degrees so it's standing on its thin edge, apply the exact same vertical load, and it barely moves. You haven't added a single gram of plastic, but by increasing that yaw distance, you've given the material more leverage against the applied bending force.
That structural leverage is the exact mechanical reason.
Yeah.
Wide flange shapes, like your classic I-beams, absolutely dominate construction.
Right.
If you compare a solid square bar to a wide flange beam that has the exact same cross-sectional area, the efficiency of the wide flange is just staggering. You're taking a bulk of the steel and pushing it as far away from the neutral axis as is physically possible.
Concentrating it all into the top and bottom flanges.
Exactly. You maximize that resulting in a massive moment of inertia without carrying the dead weight of a solid core. The web in the middle, it just needs to be thick enough to handle the shear forces and, well, keep those two flanges apart.
Which is brilliant. But even with those highly optimized shapes, structural limits are still absolute. Engineers draw a very hard line between allowable stress and damaging stress.
They have to. Allowable stress or working stress is that safe upper limit calculated for expected service conditions.
But damaging stress isn't just the point where a beam physically snaps in half.
Oh, far from it. Damaging stress is the threshold where the part simply can no longer perform its designated function.
So, like, it bends and stays bent.
Yeah, excessive yielding, where the part deforms permanently.
Yeah.
Or it could even mean high temperature creep, where the material slowly flows over time under a constant load. The buffer between the allowable service limit And that threshold of permanent deformation is the factor of safety.
Which accounts for what, exactly?
Unpredictable dynamic loads, minor variations in the material properties, or even just manufacturing defects.
Right, the stuff you can't perfectly model. But that raises a critical scenario. What actually happens mechanically when we push a highly optimized ductile steel shape past its yield point?
Well, the analysis of the plastic moment in the plastic section modulus basically maps out the anatomy of ultimate structural collapse.
Okay, walk me through that.
Under standard elastic bending, the stress profile looks like two triangles pointing at each other. The stress is highest at the extreme top and bottom outer fibers and tapers down to zero at the neutral axis in the middle.
The column in the center.
Exactly. But if you keep increasing the bending moment on a ductile beam, those extreme outer fibers reach their yield strength. They hit a ceiling. They literally can't take any more stress, but because the material is ductile, they don't fracture.
They just begin to stretch plastically.
Yes.
And so as you continue to add load, the adjacent fibers deeper inside the beam, they start to hit their yield point as well, right?
Yep. The yielding progresses inward from the flanges, moving steadily toward the neutral axis.
So the stress profile completely changes.
Right. It changes from those triangles into a solid rectangular block of maximum stress. Eventually, the entire cross-section, from the top flange all the way down to the neutral axis and from the bottom flange up, has completely yielded.
Wow.
When this state is reached, the beam just can't resist any additional bending moment. It forms a plastic hinge.
A plastic hinge.
It hurt
So
me.
the beam behaves as if it literally has a mechanical hinge pinned at that location, folding under any further load.
Precisely. Designing for ultimate strength requires calculating that fully plastic bending moment, so you know the absolute ceiling of the structure.
Okay, so we've established how a wide flange shape creates massive leverage against bending. But, forces in the field rarely act in just one clean vector.
Almost never.
Right. If the wind catches an asymmetrical structure or a drivetrain applies torque to a shaft, you introduce twisting. And twisting completely breaks the rules we just established for simple bending, doesn't it?
Oh, torsion is an entirely different mechanical beast. The fundamental divide in mechanical engineering here is whether you are twisting a solid, perfectly circular shaft or literally anything else.
Because circular is easy.
Yeah, when you apply torque to a circular shaft, the geometry behaves beautifully. Plane sections remain plane. You can visualize the shaft as a stack of flat poker chips.
Okay, poker chips.
As you twist the cylinder, those chips simply rotate relative to one another. They stay perfectly flat, and the shear stress increases linearly from zero at the center to a maximum at the outer surface.
Super clean. But twist a square bar, an I-beam, or an angle iron, and the assumptions of circular torsion just fall apart completely. The cross-section doesn't stay flat, it warps.
Exactly. The corners and edges distort and twist out of plane. Because of this longitudinal warping, the shear stress distribution becomes intensely complex. It is no longer uniform, and it is no longer proportionally tied to the distance from the centroid.
Wait, really?
Yeah, the maximum shear stress in a twisted rectangular bar actually occurs at the midpoints of the longest sides, not at the furthest corners.
That is wild, and calculating that complex warped stress field analytically was a massive historical bottleneck, right? To solve it, engineers turned to the soap film analogy, developed by Ludwig Prandtl. And I have to push back on this concept initially.
Let me guess, it sounds totally crazy.
Yes. Wait, you're telling me a delicate soap bubble actually helps an engineer calculate the twisting strength of a solid steel beam? Because, that sounds completely absurd.
I know, it sounds like a weird anecdote, but it relies on a profound mathematical identity.
Mm.
Prandtl realized that the partial differential equation governing the shear stress function in a twisted elastic bar, specifically the Poisson equation,
Okay.
it's mathematically identical to the equation governing the deflection of a stretched, homogeneous membrane subjected to a slight uniform lateral pressure.
So it's basically a physical cheat code for a multivariable calculus problem. To calculate the twisting strength of an irregular structural shape, you literally cut a hole in a flat plate matching the exact cross-section of that shape. You stretch a thin membrane, like a soap film, over the hole and inflate it slightly from below with uniform air pressure.
And the geometry of that inflated bubble gives you the complete stress profile of the steel.
That is just, wow.
The total volume of air trapped under the inflated soap film is directly proportional to the torsional rigidity of the beam, the total torque it can carry. Even more critically, the slope of the soap bubble at any given point is directly proportional to the magnitude of the shear stress at that corresponding point on the steel beam,
So where the bubble is steepest,
which is usually at those midpoints or internal corners.
that's where the steel will experience the highest stress.
You got it.
That proves that nature's underlying rules for tension, curvature, and energy minimization just apply universally across scales. It works for a fragile film of soapy water just as accurately as it works for a massive structural member.
It really is beautiful. And the mechanics of torsion get even more complex when we introduce end constraints.
Like welding it in place.
Right. If you take an I-beam and twist it, but you weld the ends to massive rigid abutments so they absolutely cannot warp, the torsional capacity of the beam changes drastically. The beam fights back against the constraint.
Because it wants to warp, but it can't.
Exactly. If you physically prevent the ends from warping out of plane, you force the beam to remain flat at its boundaries. The flanges of the I-beam are trying to warp longitudinally under the torque, but because they are held back, they undergo lateral bending. They start to act like cantilever beams deflecting sideways.
So by applying a pure twisting force, you inadvertently force the top and bottom flanges to bend laterally in opposite directions.
Yes, and the shear forces developed by the flanges resisting that lateral bending vastly increase the torsional stiffness of the overall bar. Constraining the warping can increase the apparent torsional stiffness by a factor of 5 or more, depending on the length of the span.
Wow. Okay, so we can design ideal geometric shapes for bending, and we can map out twisting using membrane analogies and constraint analysis, but we can't just float an infinitely long, perfectly smooth, solid beam in a vacuum.
Sadly, no.
In the real world, you have to bolt the beam to a column, you have to drill access holes in it, you machine keyways into drive shafts. How do these necessary physical features compromise the theoretical strength of the shape?
Well, they create stress traps, officially known as stress concentrations. Anytime you interrupt the smooth flow of stress through a solid material with a sudden change in geometry, a drilled hole, a sharp shoulder, a notch, or even standard screw threads.
You create a stress razor.
Right. The severity of this localized peak is quantified by a stress concentration factor, denoted as K sub T.
You know, visualizing the stress flow through a component, it's like traffic on a highway.
Oh, that's a great analogy.
Yeah, the nominal stress is a 4-lane road moving smoothly, but a drilled hole is a lane closure. Suddenly, all the stress cars are jammed up in one spot, creating a massive spike in pressure, even though the total number of cars on the highway hasn't actually changed.
That analogy scales perfectly to solid mechanics. The total tensile load applied to the part remains constant, but right at the transverse edges of that hole, your lane closure, the localized stress can spike to 3 or 4 times the average nominal stress of the surrounding material.
That is a massive jump.
Huge. Now, for static loads on ductile materials, this is often manageable because the material can yield locally and redistribute the stress. But under repeated dynamic loading, this localized spike becomes catastrophic.
And this is the mechanism behind fatigue, right?
Yes, exactly.
If that traffic jam happens repeatedly, thousands of times a minute in, say, a vibrating engine bracket, the localized stress at the edge of the hole causes microscopic slip lines to form along the crystallographic planes of the metal.
And those slip planes experience highly localized plastic deformation. Over millions of cycles, these microscopic intrusions and extrusions on the surface coalesce into a microcrack.
And once a crack starts,
It's game over. The tip of the crack itself becomes a new, infinitely sharp stress concentration, accelerating the propagation. Fatigue drastically lowers the endurance limit of a material. A component can be loaded well below its macroscopic yield strength, but because a tiny machine notch creates a cyclic stress spike, a crack initiates, propagates, and ultimately results in a sudden, brittle fracture with absolutely zero warning.
terrifying. And a highly insidious version of this is fretting fatigue, isn't it? This occurs when two surfaces are clamped tightly together, like a steel collar press-fitted onto a shaft, and they experience microscopic relative motion under an oscillating load.
Right. The surfaces rub on a microscopic scale, causing localized micro-welding and tearing. This tiny localized chafing causes surface pitting and oxidation.
Which acts as a notch.
Exactly. The surface damage acts as a microscopic notch, a perfect stress razor that initiates a fatigue crack. Fretting can snap a massive, seemingly pristine steel drive shaft in half purely from the microscopic friction at a mounting point.
So stress concentrations are driven by geometry, but dynamic stresses are driven by motion. Which brings us back to the paradox of the spinning turbine blade from the intro. What happens when the part itself is moving at high velocity, generating inertial stresses?
Well, looking at the mechanics of a rotating, homogeneous circular disk, like a flywheel or a jet engine rotor, every particle of that mass is experiencing centrifugal force as it spins. The inertia of the material constantly wants to travel in a straight line, pulling outward away from the axis of rotation.
So the stress is generated purely from the object's own mass resisting the centripetal acceleration.
Yes, this creates a biaxial stress state. Radial stresses pulling outward from the center, and tangential or hoop stresses pulling along the circumference. And counterintuitively, the highest stress is not at the outside edge where the linear velocity is highest. The radial and tangential stresses hit their absolute maximum right at the dead center of the disk. The entire mass of the spinning disk is pulling outward on that single central point.
The center, the point with zero linear velocity, is where the disk is fighting the hardest against tearing itself apart.
Exactly.
And this is where the math converges on the ultimate danger zone, because if you need to mount that spinning disk onto a drive shaft, you have to drill a hole dead in the center.
Right. You take the maximum dynamic inertial stress of the rotating mass, and you combine it with the massive geometric stress concentration factor of a hole. The tangential stress at the edge of a central bore instantly doubles compared to the stress at the center of a solid disk skidding at the exact same speed.
Wow. So traditional homogeneous materials like steel and aluminum are fundamentally trapped by these geometric rules. They are just bound by stress concentrations, warping effects, and fatigue limits. To bypass these hard limits, engineers have to stop finding isotropic materials in nature and start weaving their own.
That's the only way forward.
And this requires a massive shift from classical metallurgy to the anisotropic mechanics of composite materials.
Right, because isotropic implies the material has identical mechanical properties in all directions. A billet of aluminum provides the same stiffness, whether you pull it axially, laterally, or diagonally. But anisotropic composites have properties that are entirely dependent on the direction of the applied load.
Because the material's internal anatomy is engineered specifically for that load path, we are literally building the structure at the micro level.
Precisely. A composite consists of two primary constituents, the reinforcement and the matrix. The reinforcement takes the form of continuous microscopic fibers like carbon, aramid, or glass.
Which are incredibly strong.
Immense tensile strength and stiffness, but strictly along their longitudinal axis. You cannot push a string, and a bundle of dry carbon fibers has zero structural rigidity in compression or shear.
Right, so to stabilize those fibers, they are embedded within a matrix, typically a thermosetting polymer resin like epoxy. The resin's role is to hold the fibers in their engineered orientation, protect them from environmental degradation, and crucially, transfer the applied load between the millions of individual fibers via shear stress at the fiber matrix interface.
So a single layer of this composite apply is incredibly strong in the fiber direction, but very weak transversely, where only the resin is taking the load. To create a usable structural component, engineers stack these plies at various angles to build a laminate.
And modeling the mechanics of this stack relies on classical laminated plate theory, or CLPT, right?
CLPT is the mathematical framework for predicting how a stack of highly directional plies behaves as a unified plate. In an isotropic metal, you can predict elastic behavior using just two constants, Young's modulus and Poisson's ratio.
Super simple.
Very simple. But for a composite laminate, the stress-strain relationship is defined by massive stiffness matrices. And the most critical and potentially dangerous of these is the B matrix.
The membrane-bending coupling matrix.
Exactly. If the stacking sequence of the plies is not mathematically balanced, the B matrix will be non-zero. A non-zero B matrix means that purely in-plane forces, like applying simple tension along the edge of the panel, will actually induce out-of-plane bending or twisting.
So if I don't balance the laminate, pulling it one way makes it warp in another. It sounds exactly like pulling on a bias-cut dress, or that bimetallic beam effect we saw earlier where temperature makes it curl.
It is exactly like the bimetallic strip. If you have fibers aligned at 0 degrees on the top surface and 90 degrees on the bottom surface, applying simple tension creates a completely unbalanced stress field. The top ply resists the pull differently than the bottom ply, and the entire flat panel just warps.
So how do you fix it?
To eliminate this coupling, the laminate must be designed with rigorous mathematical symmetry. Engineers define a stacking sequence to intentionally drive the elements of the B matrix to 0. They create a symmetric laminate.
Okay, what does that look like?
For every single ply laid at a specific angle and specific distance above the midplane of the laminate, An identical ply is laid at the exact same angle and exact same distance below the midplane.
Ah, so you are physically mirroring the material architecture to cancel out the internal warping moments.
Exactly. And from there, engineers utilize quasi-isotropic laminates. By stacking the plies at mathematically balanced angles, commonly 0 plus or minus 45 and 90 degrees, and making the stack symmetric, the resulting composite panel actually mimics the uniform, multi-directional in-plane stiffness of a sheet of steel or aluminum.
But at a fraction of the mass.
Exactly. The load is distributed seamlessly across the tailored angles.
So they're tailoring the stiffness ply by ply, zeroing out the structural coupling, and building a custom supermaterial that places structural reinforcement exclusively along the required load paths.
It really represents the ultimate convergence of material science and structural geometry.
It's unbelievable. So we started today by analyzing the fundamental geometry of bending, seeing how wide flange shapes maximize their moment of inertia for exponential structural leverage. We mapped the complex warping of torsion using Prandtl's soap film analogy and saw how boundary constraints force flanges to act as cantilevers.
We covered a lot of ground.
We really did. We navigated the microscopic traffic jams of stress concentrations, fatigue cracks, and the extreme inertial stresses locked inside the center of a spinning disk. And we finished by breaking the rules of isotropic metals entirely, weaving custom composite laminates to perfectly counter the B matrix.
You know, the progression from geometric optimization to material synthesis completely changes the definition of structural limits. And looking forward, this progression is accelerating.
Oh, for sure.
We talked about designing composites by manually layering flat plies at different angles to handle stress. But what happens in the near future when we can 3D print composites at the microscopic level, continuously curving and varying the fiber directions perfectly along the invisible stress trajectories we discussed earlier?
That would eliminate the stress concentration factor entirely.
Exactly. Will standard structural engineering handbooks even apply anymore when the material itself is a living algorithm?
When the geometry, the stress flow, and the molecular orientation all merge into one mathematically perfect shape, that is an amazing thought to leave on. Keep your tolerances tight and your curiosity open. We'll see you next time.